My name is Isaac Wachsman, and this is my semester research project. My title is Running in Place Static Code Analysis. So first, for the problem formulation, in this infographic we'll be discussing static code analysis, which is the process of analyzing source code before it's run, and this is usually done to find security vulnerabilities, but it could also find other just general errors and compiler errors and just fix the readability of code. So this topic is covered in Module 12 of the course and Chapter 13 of Somerville's textbook. I chose to cover this because I like algorithms and mathematics, and these static code analysis tools use a lot of algorithms, pattern matching, stuff like that, to detect vulnerabilities in code. I wanted to learn more about how this worked. So in this infographic, I covered automated code analysis and pattern-based vulnerability checks, and I did not include runtime analysis or manual code analysis. So next up, for the literature search, I found 3 papers that deal with these static analysis tools. So the first one claimed that static analysis tools are generally compared using fake data sets. So this paper evaluated different tools using 1.2 million real lines of code and showed that up to 80% of vulnerabilities might be missed by these tools. The next one was talking about how graph neural networks have made their way into the static source code analysis tools, and future opportunities to use machine learning in code analysis include analyzing additional artifacts other than source code, and also paying more attention to the interpretability of code rather than just if it's safe or not. And then finally, this last paper showed that recent work has introduced pre-trained language models into static source code analysis tools, but these might not be the most precise and might miss a lot of the vulnerabilities. So this paper introduces a hybrid technique that combines traditional and new techniques. So from reading these various sources, it became clear that static code analysis is a major component of software engineering that is going to become even more important in the future because software will become larger, more complex, and then the threats that come to our software, like hacking and malware will also become more powerful. So most code analysis in the early computing age was manual, but these tools were soon built to look for vulnerabilities in source code, and the early tools used regex engines and pattern matching to identify vulnerabilities. So the problem with these early models is that they would flag code that has already been established as vulnerabilities, but it couldn't find new patterns in code that were vulnerabilities. So people started using neural networks and large language models in static code analysis tools to use artificial intelligence to identify potentially unsafe code. However, to my surprise, 2 of the papers that I read stated that the modern analysis tools actually lack precision and miss a lot of vulnerabilities. So there's currently debate about how these tools should be implemented. So in my opinion, for the evaluation, even though these tools might not be super precise right now, I believe that artificial intelligence is still in its infancy, and it will continue to become more efficient and effective in years to come. We've already seen the power of models like GPT, and they have been growing in power exponentially in recent years. It shouldn't be long before these static code analysis tools become very good at identifying risks with AI. We can't continue using traditional techniques because the programs are going to be so complex and slow when they're working on enormous code bases. What I find most interesting is how artificial intelligence and machine learning are being leveraged to detect vulnerabilities in source code. This is extra important because these techniques will allow the tools to find new patterns for vulnerabilities, not just ones that we already know exist. So finally, I have some figures here. This first figure shows vulnerabilities by type in the 1.15 million lines of source code analyzed. The most common ones were out-of-bound operations, followed by null pointer dereferencing. And then this figure from the second article shows an overview of how neural message passing works in neural networks. And here are my references, and that's all. Thank you very much.